Chapter 4. This is the motion introduction, which is information covered not in your textbook. So if you look at this diagram here, take a look at this picture, and then look at this picture, and look at the first picture again, second picture, and you'll notice a difference. And the difference that you'll see is that Saturn did move. So that's what changed, but how do you know that changed? What you were looking at is using this line or other things that did not move as your frame of reference. And a frame of reference is a system of objects that are not moving with respect to one another. So when you're sitting at a stoplight and you're in a car and you're sitting next to a semi, sometimes you'll feel the semi will pull away and you'll feel like you're going backwards. What is one of the first things that you do? I, as a driver, press harder on the brake. But what you'll do is you'll look outside of the car and look at an object. The object that you look at to know if you're moving needs to be still. And that is the key thing with a frame of reference, is that they are a non-moving object. So looking at another car is not really going to be a good comparison to know if you're moving or not. When we look at this picture, can you really tell how big that this object is? We don't have any reference of what the distance is from us to this object, so it's really hard to estimate what size it is. This is actually the launch pad for the shuttle, so it is a really tall object, but it doesn't seem that tall because we are so far away at a greater distance. Same thing with this. You look at this object and you're thinking just how really big that is, and it seems very big in diameter, but unless you have something to compare it to that you are familiar with the size, you're not sure. So if I move this picture up and you look at a person, that gives you a reference point of how big the back part of the shuttle is. Same thing with the emblems hanging from the ceiling. You move the emblems up and see a person to compare it to. A standard size of a person compared to an emblem hanging from a ceiling, it's a big difference. So you need things to compare to know what size they are. Geologists will use a scale in their picture to tell you how big an object is that they're taking a picture of. They put a person in the picture to show reference of how big it is. They have a person standing in the picture. They have a quarter in the picture, or a pencil, or a hammer. A lot of people think, oh, they left those there on accident. No, they put them there on purpose, so you know actually how tall this structure, this object is in comparison. So when we talk about relative motion, this is the movement depending on the frame of reference. So how is an object moving? You're going to look at the object that is not moving, the frame of reference. So that is relative motion. Frames of reference and relative motion is actually the reason that people get car sick. Your brain is getting two different sets of information about your body's motion that might not exactly agree with each other. Information from your eyes and information from your inner ear. Some people are more sensitive to these differences, which causes them to feel car sick as they watch the road whiz by. If you are prone to getting car sickness, try to look forward at a point far in the distance and stay focused on that. So that's the key thing, is that's why most of the time people who get car sick like to sit in the front seat, and they get more car sick if they sit in the back seat because they're not able to find that focal point as well sitting in the back as they can in the front. It's a very similar thing with ballet dancers and ice skaters is when they do their spins. They find a focal point, and it's called spotting, and they will find a spot and look at it and turn, and as they turn their head and go back to that same spot. And this is supposed to prevent them from getting that dizzy, spinny feel that you will get when you're like when you're in the car. It's because your inner ear is not communicating correctly with your brain and saying, okay, I'm okay, I'm in balance. We look at vectors. Vector is a fancy word for arrow. These are arrows that represent motion. They can show direction, distance, and force. So obviously the arrowhead shows you the direction. The distance is shown by the length of the arrow, and the force can be shown by the size of the arrow. When you look at some vectors that are combining together, if they are going in the same direction, and this could represent distance or it could represent force also. So if you have 5 plus 5, they will add together and give you 10. Now if they're in the opposite direction, one going right, one going left, and left is obviously shown with a negative number, they will cancel each other out and you get a result of 0. And again, they don't have to be the identical numbers. It could be 5 and 10 will give you 15. Or if you have 5 to the right, 10 to the left, only 5 to the right cancel out, leaving you with a remaining motion of going to the left 5. So I would take a few of these and write down examples of adding vectors. Now note that they don't have to be horizontal, it could be vertical. They can be going up and down. So take a moment and write a couple of these down on your note taker as examples. Distance is the length between 2 points, measured in meters or miles. We usually stick with meters because we are talking about science and we use this SI units. So there's a difference though, but when we're talking about distance and displacement. When I talk about distance, I can tell you that I live 3.2 miles from the school. Now that is the distance I would take driving in my car on the road to get to my house. Displacement, though, is the direction from the starting point to the ending point. This is the length of a straight line from finish to start, or point A to point B. So if I told you that my house distance was 3.2 miles, but it may only be like 1.3 if I did my displacement from the school straight to my house, as if like a bird flew there, because they don't have to follow the roads. It's kind of like the same thing of flying in an airplane. If you drive to Florida versus flying to Florida, it's a different pathway that you take. The car, you have to do distance because you have to follow the road. Airplane takes the displacement because you can take a straight shot. When we look at distance and displacements, if we look at this car travels 4 kilometers and then it travels another 2 kilometers. So these two will add together to give you a total of 6 kilometers at the finish. Now the 6 kilometers is your distance. But because the car started and finished at the same spot, this is also your displacement. So there is times that your displacement can be the same as your distance. Now we take situation B, and we take our car and we drive 4 kilometers to the right, and we drive 2 kilometers back. Now, when we look at our distance that the car drove, you add them up. So it went 4 kilometers to the right, plus it went another 2 kilometers to the left, so it did go 6 kilometers for distance. But the displacement is going to be different in this situation. You go to the right, you start here, but then you finish here, so it's really you finished and only traveled 2 kilometers. So in this case, your displacement is shorter than your distance. When you look at how a maze, this is a good example to show you displacement and distance. So if we help our butterfly find his way to the flower, we usually draw one line. Now we can take this and make it solid lines, and this would be a vector, and this would be a vector. So depending on your situation, you can reference these as from point A to point B. This is the displacement. So it's showing you direction because it has an arrowhead, and it's also showing you the side, the distance that you're going, because depending on your arrows that you draw, we'll go through the whole thing. So this whole path is called distance. But we know butterflies don't have to follow a path, they can fly straight. So if the butterfly went straight across, this would be the displacement. So if you were giving a friend directions to your house, displacement is shown with a resultant vector. So a resultant vector is the overall displacement from start to finish. If you just used distance and told me that my house is 3.2 miles, I would not know what direction to go. But if you told me using displacement and using vectors, it would give me a direction. So you would have to use displacement to tell me how to get to my house so I know what direction to go. But the directions in displacement would include multiple displacement vectors. So this would be 1, this would be 2, this would be 3. So you can show displacement for short routes, and then the resultant vector is from start to the finish. Okay. For an example here, suppose we have two towns, A and B, 10 kilometers apart, but either side of a hill. They are joined by a railway line that is straight and goes through the hill in a channel. The road goes around the hill, and the total journey distance is 25 kilometers. Okay. So if I say town A is my house, and town B is my grandma's house. If I go to grandma's house and I take the tunnel, what is my distance? Well, the tunnel goes straight from town A to town B, so it is 10 kilometers. And what is my displacement? In this scenario, my distance is the same as my displacement because I followed a straight path. But it rained a lot, hence like it has been now, and the tunnel flooded. So instead of taking the tunnel, I have to go to grandma's house and follow the road. So I follow the road to grandma's house. This time my distance is not 10, but it is 25 because I took the road. But what is my displacement? My displacement is still 10 because this is my starting point and this is my finish point. Now this time, if I went to grandma's house and took the road, and I visited and I came back to my house, what is my distance? Well, you have to think about, I went there and back, so it's 25 plus 25. So my distance is 50 kilometers. But what is my displacement? Remember, I started here and I finished here. So this time, my displacement is 0. So technically, I didn't move because I started and finished in the same exact spot. So you need to understand the difference between distance and displacement. What you will be assigned is you will be given a school map, and on this map there's a second floor and a first floor. You will be using the white day or the blue day depending on when you have this class. So you will take your schedule, and then you're going to mark your path through the entire school from when you enter the building. So if you come into the commons, that's where you're going to start. Then if you go to the commons and go to the gym, you're going to mark your path. Then you go to your locker, and then you're going to follow your daily schedule from first block to second block to third block to fourth block. You will not show stopping at the drinking fountain. You will not show going to the bathroom, and you will not show yourself stopping at locker stops in between the classes throughout the day. The only time you go to your locker is the first thing in the morning, and then you'll go throughout your day. You'll need to make sure that you are aware of the stairways so you can go from the first floor to the second floor. You will be finding your total distance, and you will be finding your displacement for your traveling. On the map, there is a scale, and you are to use that to figure out what your distance is. We ask that you use a different colored pencil for each block. And I would use pencil and no pen or markers because they will bleed through. And you need to be able to keep track of your path so when you go back and measure it, it's easier to do. So this will be your assignment to complete the understanding of distance and displacement.